Dia City has a connection to the Sudbury Neutrino Observatory that goes back all the way to the earliest days of our conference. I think it was in 2000 or 2001 that we learned of this vast pool of purest water 2 kilometers below the surface of Inco's Creighton mine in Sudbury. And it was there that the teeny tiniest subcomponents of matters, we thought, could be fleetingly detected. So Mark Chen grew up in that project, and today he's in charge of going beyond it to try and find the mysterious dark matter that is believed to be a huge part of the makeup of the universe. So in that sense, Mark and Canada and CIFAR are leaders in the quest for a greater understanding of the universe at the most microscopic levels. Mark Chen.
Thank you. So we live in a dark universe, and it's only been recently, meaning within the past few years, that physicists have started to get an idea about this dark side of the universe. Although we really don't know that much about it, but we're going to go after it and try to detect this, this dark component of our universe. And so I'll tell you a little bit about some of our efforts and the worldwide effort on this. So I'll start with Universe 101. So the universe is thought now to have the following composition. Less than 5% of the universe is made of atoms, normal matter, the same stuff that makes up you and me. And so when I talk about dark matter, I should note that there's several levels of this dark matter problem that exists in cosmology. So of the roughly 5% of the universe that we know consists of ordinary matter, only about 10% of that is luminous in stars. So when we look at the night sky and we see the light, we see the stars and the galaxies, the matter that's in those stars, it maybe is about 0.4% of the total matter energy density of the universe. And so the rest of it is dark, but not in the same sense. We can detect that other matter. We see neutral hydrogen by looking with radio telescopes and seeing the emission in radio. We can see dust with infrared. We can see hot gas with X-ray satellites. So this is matter we know about, and although some of it is dark, but that's not the dark matter that really concerns cosmologists, that concerns physicists. So it is the rest of the universe that we really know quite little about. About 23% of the universe is made up of some other type of matter that is different than the matter that's the ordinary matter, and that's called dark matter. And I don't have time to talk about the even more mysterious dark energy, which is the dominant component of the matter energy density in the universe. Okay, so how do we actually see this dark matter? How do we know that it's there? It comes about through this technique called gravitational lensing, and in fact called this weak gravitational lensing. So what happens is that gravity warps space-time, and so paths of light paths are bent as a result. And so a galaxy that's in the background will have its light distorted as it passes, as that light passes nearby galaxy or cluster of galaxies in the foreground. And so gravitational lensing, here you'll see these arcs of light that are the arcs, the distorted views of background galaxies as that light has passed nearby this foreground, and that light has curved. So if we go back to the weak lensing concept, you don't see these arcs in that previous view, but now through observation and impressive computational astrophysics, we can see the distorted shapes of those background galaxies, map the correlations of this shear, and then thereby determine the total matter density, including the dark matter that's present in several different instances. And so in that bullet cluster example, we can see that dark matter. Okay, so what do we know about this dark matter? Okay, so we know it's there. And we know it is not the same as the ordinary matter. It is non-baryonic is the terminology. So it's not the same stuff that makes up atoms and nuclei that we're familiar with. And this dark matter is practically collisionless. It has little interaction. But it does have does interact gravitationally. So the dark matter, in fact, clumps due to self-gravity. And in fact, it's the clumping of the dark matter that provides the seed for the ordinary matter to clump that then forms the structure that we see in the universe, galaxies and stars. And then we also know that these particles of this dark matter are cold, and that's the terminology, that they're non-relativistic. Okay, so that's what we know about this dark matter. It's easier to describe, though, what we don't know, is that we don't know exactly what these particles are. Okay, that's what we want to find out. There are some ideas that these particles, some of the leading ideas are these ones here. They could be the particles predicted by theories that include this concept called supersymmetry. They could be the excitation states due to the presence of higher dimensions. And so then those particle states then could constitute some fraction of the dark matter. They could be this other particle called the axion that comes about as that solves another problem in particle physics. But we really don't know exactly what these particles are. But we want to go after them, and we want to see what we can learn about them, because we know that they're really there. Okay, so the dark matter hunt begins, and in fact, the start date for the dark matter hunt, I would say, is 2008. And there are three efforts that are really quite different that I'll discuss. And so three different ways that physicists and astrophysicists are going to try to go after this dark matter problem. Okay, so in 2008, there's the launch of GLAST, and GLAST is the Gamma Ray Large Area Space Telescope. In 2008 also will be, towards the end of 2008, will be the turn-on of a very large particle accelerator called the Large Hadron Collider, or LHC. And in 2008 in Sudbury, we will complete SNOLAB. And so I tricked you there, SNOLAB is not an acronym. And so SNOLAB is significant because we're in the process of building what will be the world's deepest underground lab for particle physics. And that's significant because depth is absolutely necessary if you want to detect these very rare particle phenomena. So at the surface, there's a shower of particles that bombard us all the time, cosmic radiation. And so to give you an idea what the rate is of this cosmic radiation, it's about one that passes through the area of your hand per second. Okay, so by going deep underground, you'll screen your very large detectors from this cosmic radiation, suppressing it by factors of millions or tens of millions. And so you need to be far deep underground so that the background radiation and the signals you see in your detector are small enough that will allow you to detect the potential interaction of dark matter in your detector, which might occur at the rate of one such dark matter detection per year per ton of detector that you've instrumented. So Sudbury Neutrino Observatory was the effort that took place over the past 20 years. Really, the construction of SNO began in 91, and the SNO detector turned on in 99 and operated for 7 years. And with SNO, we detected neutrinos, which are we now understand a lot about neutrinos, and we now know that neutrinos are not the dark matter. Okay, but and so with the success of SNO, we were able to launch. There we go. We were able to launch into the expansion of the underground facility, and so this is the thing that we call SNOLAB. And so this is the SNO detector. It is so the blue sphere that you see is 40 feet in diameter and contained 1,000 tons of this ultra-pure water Moses was telling us about. And so this is a very large cavity that exists underground 2 kilometers in Inco's Creighton mine. Creighton is an active mine, so when we go down to work at the detector, we ride the cage with miners. So it's quite a trip and very, very interesting to descend into the mine and to walk through the drifts in the mine in, mining environments, very dirty, and then suddenly to emerge into a pristine underground laboratory, which is ultra clean in order to allow us to build the sensitive detectors that we do. And so this is the expansion. It's this part that's new and that we're completing this year, and it includes large space for similarly sized experiments like SNO, and also smaller space to develop prototypes and other smaller experiments. So this is what we call SNO Lab. Total budget for this was 50 million Canadian dollars. Okay, so what is the main challenge? What do we do then with what are we faced with? We have we have this is the starting point. It's digging rock out of a mine and creating these enormous spaces, but then transforming this into this pristine low background laboratory. So that's the main challenge that we have. And had that movie worked, you would have seen what that looks like with SNO. But unfortunately, I don't have that material to show you. But this is then what we'll do in SNO Lab. We will build new dark matter detectors, and I don't have really time to go into the details what these dark matter detectors do, but I'll give you an idea of what they're like, what the technology is like. So for example, we will aim to build a large tank that will contain 3.6 tons of liquid argon, okay, with this ultra pure liquid argon, with these dark matter particles that they're passing through us. Presumably they're passing through us all the time. Then occasionally, so they'll pass through into the mine, through the rock, without being impeded, because their interaction is very weak. But occasionally they may interact with the argon and then produce a flash of light. So we'll try to detect that flash of light at the rate of 1 per ton per year. Okay, other dark matter detectors that will go into SNO Lab include crystals of germanium that will be cooled to millikelvin temperature. So these cold pieces of germanium, when a dark matter particle hits them, it will cause them to heat up a small amount. And by detecting that temperature rise, you can perhaps detect the potential interaction of dark matter. There are also detectors which contain superheated drops of freon dispersed in a gel. And then when the dark matter particle hits this, it causes this superheated drop to expand in the form of a bubble, and you hear a little popping sound. So instrumenting this gel with microphones to listen for the sounds of dark matter hitting your detector. Okay, so then that's the end of what I wanted to say. Let me give my closing comment, which is, and so this is very hard for a Canadian to say because Canadians we're supposed to be very modest, but this is tremendous that we're doing this in Canada, that we can have a leading effort to go after one of the most fundamental questions in physics, to go after dark matter that competes with the largest laboratory in Europe and that competes with missions that go up in space. And so, it's difficult, but I'm tremendously proud that we have this effort here in Canada. Thanks.